Imagine an abyss buried in permanent darkness at the moon's south pole, where temperatures plunge to minus 200 degrees Celsius. In 2026, Beijing will launch the Chang'e 7 mission, carrying an extraordinary machine. It is a hopping robot built for one purpose only: to drop straight into those black, deadly craters and search for molecules of water ice. Why would a superpower gamble billions of dollars just to throw a robot into an abyss? Because the truth is, they are not going there to collect rocks or plant a flag. They are hunting the oil of the 22nd century. What makes those frozen crystals more valuable than any gold mine on Earth? To understand why these ice-filled craters matter, we need to look back at how two superpowers approached the sky. In the 20th century, America's Apollo program was a magnificent sprint. They put humans on the moon, collected rocks, planted a flag to prove national greatness, and came home. It was the era of bringing your own packed lunch on an expedition. But China's Lunar Exploration Program, or CLEP, follows a completely different philosophy. They are not running a sprint, they are running a marathon. Instead of rushing astronauts to the moon for prestige, Beijing has spent decades sending robots to build three-dimensional maps of the surface and test the technologies needed for a permanent foothold. They are entering the era of settlement and infrastructure, where in-situ resource utilization, or ISRU, is not a luxury. It is a survival requirement. For the average American, this shift is no longer science fiction. It will determine whether trillions of dollars in taxpayer money are wasted, and whether the next generation of American engineers loses millions of high-tech jobs to a monopolized supply chain controlled by Beijing. And that supply chain begins with the most basic laws of physics. Has the US spent too long sleeping on its Apollo victory while a new order quietly takes shape? To dominate the space economy, you first have to overcome one brutal barrier of nature: Earth's gravity well. Right now, the cost of launching even a single kilogram of cargo out of our atmosphere is outrageously high. Most of the weight of a rocket sitting on the launch pad is not the satellite or the astronaut. It is the fuel needed just to escape Earth's pull. But the moon is different. With only 1/6 of Earth's gravity and no atmospheric drag at all, launching a spacecraft from the lunar surface into deep space, including missions to Mars, requires far less energy. In aerospace physics, this is known as the delta V problem. Whoever masters the moon's shallow gravity well will hold the key to opening the gateway to the solar system. But to turn the moon into a transfer hub, you need fuel. That is exactly why the major powers are targeting the lunar South Pole, especially the permanently shadowed regions that never face direct sunlight. At the bottom of those dark, ultra-cold impact craters, scientists believe there may be frozen water. If that ice can be extracted, it can be split into oxygen for astronauts to breathe and liquid hydrogen for rocket propellant. In reality, the moon's South Pole is a giant oil field for the new century. But the moon's dark regions come with a communications nightmare. They are completely blocked from direct contact with Earth, which means radio signals cannot get through. You cannot control a fleet of mining robots if you cannot even call them. To break through that deadly blind spot, China made an astonishing infrastructure move. Years before a Chang'e spacecraft was ever supposed to land there, Beijing quietly launched the Qichao Relay satellite system into space. These satellites were placed in a long, frozen elliptical orbit, acting like radio lighthouses hanging behind the moon. They received signals from robots sitting deep inside the ice craters and bounced those signals back to Earth, creating a continuous connection with no interruption. While the West was still arguing over budgets, China had already built its own satellite internet network for the dark side of the moon, with the Qichao system serving as eyes and ears and polar ice serving as fuel. Beijing has drawn an exceptionally complete blueprint for a space gas station operating in 1/6 of Earth's gravity. But on paper, everything always looks perfect. The real test begins when the machine touches the surface. Splitting water in theory is one thing, but how do you build an automated factory in a place with no atmosphere at all? And finding water ice is only half the equation. To turn a barren crater into a permanent logistics port, you cannot keep launching construction materials from Earth through silent space forever. Imagine trying to build a giant base by shipping every single brick from another continent across a stormy ocean, using the most expensive rockets on Earth. That brutal operating cost would instantly crush the budget of any nation. That is why Beijing is aiming for something far more ambitious and potentially revolutionary: three-dimensional printing structures directly from the moon's own dry, dusty soil. According to detailed plans released by China's space system for the Chang'e 8 mission in 2028, they intend to test a robotic system capable of scooping up surface material known as regolith. The system would then use high-intensity lasers or concentrated optical energy to melt that fine powder at temperatures reaching thousands of degrees Celsius. Once the regolith becomes molten, it can be extruded with extreme precision, layer by layer, to create eco-bricks or print solid domes capable of shielding sensitive equipment from deadly cosmic radiation. If they can make this ISRU technology work, the moon will not just be a fueling station. It will become a permanent industrial site supplying its own building materials. This is where we need a brutally realistic mechanical reality check so we do not get fooled by elegant promises. Blueprints always look smooth on paper, but the truth is that mining lunar dust on an industrial scale is an engineering nightmare no one has fully solved. Regolith is nothing like the soft sand on Earth. Because the moon has no atmosphere, no wind, and no running water to wear things down over billions of years, every grain of dust remains razor sharp, like shattered glass or microscopic blades. Worse still, after constant exposure to solar radiation, those particles build up powerful static electric charges. That means this sharp dust clings stubbornly to every surface. It works its way into rubber seals, clouds, optical cameras, and steadily grinds down the metal gears of robots until they are crushed after only days of operation. On top of that, regolith is an extremely poor conductor of heat. Independent assessment reports from the German Aerospace Center have pointed out that melting this electrostatically charged dust for three-dimensional printing would require enormous amounts of electricity, far beyond what today's fragile solar systems can realistically support. Successfully casting a demo brick a few centimeters wide inside a lab on Earth is not the same as mass-producing structures with a fully automated system 380,000 kilometers away. Even so, despite every extreme physical barrier, Beijing is still determined to use Chang'e 8 in 2028 as the trial by fire for this entire high-risk industrial chain. If making these bricks costs more than simply launching them from Earth, does the whole ISRU dream collapse? China is willing to accept that brutal mechanical risk because every brick made from lunar dust serves a much bigger geopolitical game: the International Lunar Research Station, or ILRS. According to official technical documents submitted by China's space agency to the United Nations Office for Outer Space Affairs, the ILRS is not a temporary camp for astronauts. It is designed to become a highly sophisticated network of facilities operated entirely by autonomous robots for years before human beings ever arrive. Power modules, communications, relay hubs, and resource extraction workshops would be delivered one by one, then automatically linked together into a closed forward outpost. With that methodical and highly visible roadmap, the future of the moon's south pole in the 2030s revolves around three realistic scenarios. In the base case scenario, which is the most likely, China succeeds in planting the core ILRS hardware modules by around 2035. At that point, water extraction and three-dimensional printing would still be limited to proof of concept status. In other words, they would be able to demonstrate the technology, but not yet make it profitable. Even so, that alone could be enough for Beijing to establish a continuous physical presence and quietly secure control over the most valuable ice-bearing craters. In the risk scenario, the moon's brutally harsh environment wins. Ultra-sharp electrostatic dust and extreme temperature swings destroy the entire drive system of the first generation of construction robots. The completion of the ILRS is pushed back by 10 to 15 years. forcing China to scale down its ambitions and urgently seek help from allied countries to share the burden of costs that could reach hundreds of billions of dollars. But the world also has to watch for a surprise breakthrough scenario. That is the possibility that Beijing successfully develops ultra-small nuclear reactors suitable for deployment in space. If the giant energy bottleneck involved in melting lunar soil is solved, then the three-dimensional printing chain could run smoothly. At that point, China could establish a powerful industrial monopoly at the moon's south polar outposts. The success or failure of this entire mega project will depend on two core variables: whether the robots can survive extreme mechanical wear, and whether the massive stream of research capital from China's domestic economy can remain stable over the next 10 years. As this ambition keeps expanding, the US is not going to stand by and watch Beijing monopolize a resource of this value. What strategy can the West use to stop a state machine that has already been programmed with a 20-year objective? As Beijing's ambition to dominate the moon's south pole grows larger, the US cannot afford to just sit still. But instead of using state budget power to subsidize a risky, decades-long program the way China is doing with the ILRS, Washington is counterattacking with its own greatest strength: the flexibility and risk tolerance of the private sector. The historic confrontation between the US-led Artemis Accords coalition and China's ILRS system is, in reality, a life-or-death clash between two completely different execution models. On one side is a vast state-directed planning machine. On the other is the free market ecosystem of technology companies. That decisive difference has just been demonstrated in the real world. Recently, when NASA's ice-hunting lunar rover project, Viper, came dangerously close to cancellation after massive cost overruns, a private name stepped in immediately to rescue it. Blue Origin moved to take over and proposed delivering the rover, worth hundreds of millions of dollars, to the moon. The private sector directly absorbed the financial risk instead of leaving it all to the government budget. This is where the American economy shows its remarkable resilience. By opening the door fully to private companies like SpaceX and Blue Origin, NASA is turning an enormous money-burning competition into real economic contracts, forcing companies to keep optimizing the technology. As a result, everyday Americans could soon benefit from the spin-off technologies created by this brutal race, from advanced new battery materials to superior satellite communication systems. But more importantly, this strategy helps ensure that the rules for extracting space resources will never be written exclusively according to standards dictated by Beijing. The space race of the 21st century is no longer about who can get there first and plant the flag. Will the power of America's free market win, or will the endurance of China's state planning machine prevail in a world with no air? The next era of humanity will not be shaped by whoever builds the biggest rockets. It will belong to whoever first learns how to turn lunar dust into a brick. Of course, everything still depends on whether the machinery can survive the destruction caused by electrostatic dust. So when you look up at the night sky tonight, do you see a romantic celestial body or the most valuable logistics hub of the future? Are we truly ready for the day when the moon no longer belongs to poetry, but to mining corporations?